notion of a sample space.
Why is it not getting bigger? Oh,
And
well.
it's a pretty, hopefully you'll find, straightforward idea. If you're doing a trial, something that is probabilistic, a trial or an experiment, a sample space is just it's a set of the possible outcomes. So a very simple trial might be a coin flip. So if you're talking about a coin flip, well then the sample space is going to be the set of all the possible outcomes. So you could get a heads, or you could get a tails. That right over here is the sample space for the coin flip. So, and it's very useful because, for example, if these are equally likely outcomes, then and you say, well, what's the probability of the event of a heads? You say, okay, that's one out of the two equally likely outcomes. Or you could even construct, once you know all of the possible outcomes, even if they aren't equally likely, you could say, well, let's create a probability distribution. We at least know what the sample space is. We know what the possible outcomes are. Now let's think about the probability of each of those outcomes. But a lot of times when people talk about sample spaces, they tend to be most useful, I would say, when you have equally likely outcomes, like in the case of a fair coin flip, because then from the sample space, it's fairly straightforward to think about the probability of various events. But this is a simple sample space right over here, but let's make things a little bit more interesting. Let's imagine a world, so let's just put this aside a little bit. Let's imagine a world where there's a bakery, and at that bakery, there are three flavors of cupcakes, but there's also three different sizes of cupcakes. So now we're essentially looking at two different ways in which the thing that we're going to be sampling can vary. So what we're doing, let me write this down. So we have our flavors of cupcakes at this bakery, and let's say that you have chocolate. You have, let's say there's strawberry, and let's say that there is vanilla. And they come in three different sizes. So sizes could be small. Let's write it out: small, medium, or large. So if you were, and let's say, each of these flavors come in each of these sizes, or it could be the other way around. Each of these sizes come in all three flavors. So now, how do you construct the sample space? If you were to say, look, I'm going to go, I'm going to blindfold myself and walk into this bakery and randomly, somehow pick up a cupcake, and my fingers can't tell the flavor or the size of the cupcake. What are the possible outcomes for the cupcake I'll pick? And the outcome would be both the flavor and the size of the cupcake. So there's a bunch of ways to think about this. One way is you could draw a tree. You could say, okay, well, I'm going to pick three different flavors. I could either pick chocolate, I'm going to pick strawberry, or I'm going to pick vanilla. And then for each of those flavors, I'm going to pick a small, medium, or large. So you can say small, medium, large. Small, and so this is a small chocolate, this is a medium chocolate, this is a large chocolate. This is a small strawberry, medium strawberry, large strawberry. This is a small vanilla, medium vanilla, large vanilla. And so you see there's 9 possible outcomes. Once again, this is a medium chocolate. You picked a chocolate and it was a medium one. This is a large vanilla. You picked a vanilla and it is a large one. And you could have done it the other way around. You could have said, well, okay, I'm going to either pick a small, medium, or large. And then for each of those, I'm going to pick either a chocolate, strawberry, or vanilla. And I'll just use the first letters to. So I'm either going to pick a chocolate, a strawberry, or vanilla. When I write the S over here in this magenta color, I'm talking about the flavor. And if I write the S in green, I'm talking about small. So here, if you have a medium cupcake, it could be chocolate, it could be strawberry, or it could be vanilla. If you have a large cupcake, it could be chocolate, strawberry, or vanilla. So for example, this was a medium chocolate cupcake. Over here, a medium chocolate cupcake is this one, a medium
Now with me?
chocolate. It would be.
Are you loving the movie or what? Why is it not letting me go on?
Tree diagrams like this to think about.
Okay, stop talking. It's not letting me go on. Okay. Let me stop the video or pause the video a minute. Super, 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 super easy. So sample spaces, it's just probability. You've done probability before, right? One person in first grade told me they'd drawn a tree diagram, and the rest of them said they never had. What that man was drawing was the tree diagram. I'm not going to go through and read all this to you unless you just want me to, because it's super easy. This is an ordered list. This is what I used on the test. Remember we had to do, they were flipping that coin twice? And I said, well, we can land on heads, tails, tails, heads, heads, tails, tails. That's how I write it down, like that. Because it makes it a little less confusing. And then this is a tree diagram. This is what you're going to learn, you're going to draw today. Is how many different outcomes can you get? And this is flipping a coin, heads, tails, you see it? And rolling a number cube. Got it? Got it. And a little bit of vocabulary. Compound event, 2 or more simple events. And the way you read that example is what is the probability of getting chocolate ice cream and fudge. That P means probability. And then sample space is a collection of all possible outcomes in an experiment. For example, flipping 2 coins, the sample space would be, there you go, heads, 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 tails, tails, heads, tails. We good? Mm-hmm. Turn the page. Example 1. When you go get ice cream with friends, there are many choices for you to make. What flavors of ice cream, what kind of topping you want, what color sprinkles. How many different sundaes can you make when you order 1 flavor of ice cream, 1 topping, and 1 color of sprinkles from the chart below? Show all possible outcomes in a tree diagram. So we're going to draw it. You got to kind of space it out. So I got chocolate, vanilla, and strawberry. And then I can get, what kind of topping?
Fudge.
Fudge or
Marshmallow.
marshmallow. And then with vanilla, I can get fudge or marshmallow. And then with strawberry, I can get fudge or marshmallow. And then I gotta add in everybody's favorite, sprinkles. No, rainbow sprinkles are the best. So you can get chocolate, or you can get rainbow. You can get chocolate or rainbow. This is not hard, is it?
Mm-hmm.
And I'm going to show you a trick to find out how many possible outcomes there are when I finish this. And you're going to be like, why didn't you just say that? But you got to learn how to write these too. So, if I circled this R right here, what am I getting?
Rainbow sprinkles.
I'm not.
So you're getting a vanilla, fudge, rainbow sprinkle.
Good. Vanilla ice cream with fudge topping and rainbow sprinkles. How many possible outcomes are there?
12.
How'd you figure that?
Because everyone there's 2 different, and everyone has 4 different possibilities.
Yeah, so you counted them, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? You counted them. All right, so there's 12 possible outcomes. Another thing you can do is simply multiply. What's 3 times 2?
6
Times 2?
12.
So there's 12 possible outcomes.
Didn't you say?
Yes, I know. Why did I say that?
That's much easier.
Because you have to learn to read a tree diagram. I don't know that you're going to be required to actually draw one, but you do got to learn to read it. So we're going to draw a few of them. I won't make you draw them all because it is kind of easier to cheat. Hey, what are y'all talking about?
I'm not wrong.
Tree diagrams?
I said it made sense.
It doesn't make sense?
I said it made sense.
Good. Okay, on to the next one with the little sandwich there. A neighborhood deli sells sandwiches that can be made with the ingredients listed on the board below. Draw a tree diagram to show all the possible bread, meat, and cheese possibilities of if a sandwich only has 1 type of bread, 1 type of meat, and 1 type of cheese. All right, what are we gonna start with? What's our bread?
White, rye, pumpernickel.
I'd love to hear y'all say pumpernickel. White, rye, and pumpernickel. Don't ever eat it.
Really?
It smells bad.
I can tell.
So, what is our meat?
Ham.
Ham, you gotta spread this one out even more.
Turkey.
Turkey and blogna.
Yeah, blah, blah.
No, it's bologna. ham, turkey, lagna. That's why the English language is so hard. That says bologna.
That's what I'm.
Ham, turkey, bologna. Good. Now, what kind of cheese do we get? Provolone and American. Provolone and American. And I'm not gonna make you draw a lot of these. I'm just gonna make sure you get it done. Provolone, American. So instead of counting all those little P's and A's, how can you find out the total possibility?
3 times 2.
Yeah, just multiply. What's 3 times 3?
6, 9,
9. And times 2?
18.
18. And if you counted the bottom down there, you'd have 18. So if you're me, this would be your sandwich. What kind of sandwich do I like?
White bread.
White bread,
turkey,
turkey, and provolone cheese. Good. I probably did
I like
that. So, but you just need to learn how to read them and write them. Awesome. Very good. So the practice. So I want y'all to draw the tree diagram for number 1 and number 2. We'll check it and then I won't make you draw anymore. Go. Alright, so number 1. Let's compare yours to mine. You're at Carnival. One of the Carnival games asks you to pick a door, then pick a curtain behind the door. There are 3 doors and 4 curtains behind each door. How many choices are possible for the player? How many choices were possible?
12.
12. And then so I did this. I was really original. I did door number 1, door number 2, and door number 3. And then I did A, B, C, and D. I don't care what you did. I mean, if you did, what y'all do?
1, 2, 3, 4.
Well, I probably would do 1, 2, 3, 4.
I'll put Z.
C1, yeah. Or C1, 2, 3, 4. I just wouldn't use 1, 2, 3, 4 because you're already using 1, 2, 3. But again, this is so super easy, and you're not even going to be required to draw these. You're just going to be required to read them. And so I'm pretty confident.
Wait, read like the problem or read the diagram?
The diagram. But I'm pretty confident that you guys know that this is door number 3 and curtain number 4 or D or whatever. Right? Okay. Awesome. How many possible outcomes were there on number 2? 9. Good. All right, so we're going to skip all that. Go to this page right here. Using experimental data for simple and compound events and probability. So, what is a simple event? One event. One thing, one happening. What is a compound event?
Multiple events.
2.
Well, more
Yeah.
than 1. Okay, it can be 2. It can be 975. And what is an example of a simple event? Let's get something really small here and easy. Like everybody's favorite. Flip a coin. What is an example of a compound event? Flip a coin. Flip more than 1. Yes, flip more than 1 coin. Flip a coin. Roll a number cube. That's not a hashtag, that's a number sign. What about a spinner? You could do a spinner in there with it. Yeah, anything that's more than one thing, and that's kind of where we're going. Because you've done probability before, but I don't think you've done compound probability. All right, probabilities. How likely an event is. Experiment 1. Get ready, this is hard. A spinner has 4 equal sectors colored yellow, blue, green, and red. What are the chances of landing on a blue after spinning the spinner? What are the chances of landing on a red? How many blue are there? 1 out of 4. How many red are there? 1 out of 4. It's hard, isn't it?
Yeah.
It's real hard.
Look at experiment 2. A single six-sided die is rolled. What is the probability of rolling an even number, odd number?
3 out of 6.
3 out of 6 for even, but what's that simplified to?
1 out of
1/2. So it's half even, then what's odd?
half.
Half. Good. And then probability of rolling a 5. How many 5s are there?
1
1
out of 6.
out of 6. I know I'm going fast. Everybody good?
Yes.
I go too fast, you have to tell me. Experiment 3. A glass jar contains 6 red, 5 green, 8 blue, and 3 yellow marbles. If a single marble is chosen at random from the jar, what is the probability of choosing a red marble, a green marble, a blue marble, a yellow marble? Well, Will, you can't talk anymore. Will can't talk anymore. How many marbles are there?
22.
And we'll do, what are we doing first? Red?
Yeah.
How many are red?
6.
6. You have to simplify it. What is it? Everybody with me? Then we got green. How many marbles are there
5.
total?
22.
How many are green?
5.
5. And then we got blue. How many marbles are there?
22.
How many are blue?
8.
Is that lowest form?
No.
What is?
4
4 over 11. And then we got the yellow. How many marbles? And how many are yellow? Is that lowest form? Yes, it is. Grace time. So yes, it is. Yay! It's hard, isn't it?
Yeah, it's hard. Real hard.
Which of the following is an experiment?
All
All of them. Yay. We do. What is the probability of choosing a vowel from the alphabet? First, know why. How many letters are in the alphabet?
26.
26. And how many are vowels, not including Y? 5. Is that lowest form?
No.
Yes.
Yes. What if we include Y? What's our probability?
26.
6 out of 26. Is that lowest form?
No.
No.
13.
What is?
13.
3 over yell it.
3.
3 over yell it. 13. Good. That lowest form? Yes. Number 2, a number from 1 to 11 is chosen at random. What is the probability of choosing an odd number? These things on the end of your hand, what are they called? They're called fingers, right?
Yeah.
Yes. Fingers, right? Use them. 1, 3, 5, 7, 9, 11. How many is that? 6. Out of how many? 11. Is that lowest form? Yes. Number 3, 4, and 5, I want you to do on your own. How many cards are in the deck? 52. So I'll tell you that part. I want you to do 3, 4, and 5 on your own. Okay. Number 3, there are 52 cards. How many of them are a king? 4. There are 4 kings out of 52. Is that lowest form? What is? 1 over 13. Number 4. What is the probability of choosing a green marble from a jar containing 5 red, 6 green, and 4 blue marbles? How many total marbles are there?
15.
How many total marbles are there?
15.
15, and how many of them are green? Is that lowest form?
Yes. No.
What can I divide by?
3.
3. What is it? 2 fifths. What is the probability of choosing a marble that is not blue in problem 4? How many total marbles are there?
15.
And how many of them are not blue? 11. With me? Javier, what do you keep looking at? Answer me. Don't do that. What are you looking at? Huh? Jordan's jacking with you? Okay. Compound probabilities. This is where we're going. Compound probability is more than one thing happening. All right, more than one thing happening. And what you have to learn about in compound probability is that there are dependent events and there are independent events. So if something depends on something else, what does that mean?
It needs it.
Okay, it needs it.
You can't
Anyone
do
else?
without it, but it depends without it.
It can't work on its own. You can't use depend to define depend. So would you say that it affects it?
Yeah.
Yeah. So like if I've got a package of cookies and there's 10 in there and I eat one, the next event, how many cookies are in there?
9.
9. Does that affect it?
No.
Yes. It did. Yes, it did. Okay. So dependent events are events which the outcome of each event has a direct effect. Independent events are events in which the outcome has no effect. For example, if I pick a marble out of a bag of 30 marbles and I put the marble back in there and pick a marble again, there's still 30 marbles in there, right? That's independent. All right. On down the page. Situation 1, the name of 16 students are put into a hat. 9 boys and 7 girls. What is the probability of picking a girl's name first, not replacing, and a boy's name second? That is a dependent event. How many people or names are in the hat? 16. How many are, what are we doing, boy?
Girl.
Girl, how many girls are there?
7.
7. Is that lowest form? Yes, so this is girls. And then we're gonna do boys. Now how many are in the hat? No? Nope. I'm not replacing it. How many names are in there?
9.
I only picked one. How many names are in the hat? 15, because I just picked one. Is everybody with me? And how many are boys? 9. And before I go any further, I need to know if that's lowest form.
No.
Divided by 3.
What do you get?
3 over
3
over 5.
over 5. So the boys, so that's gone. The boys are 3 over 5, and the girls are 7 over 16. How do we find the compound probability in that? We've done it in beginning assignments, if anybody remembers. And probably on the test. Not maybe just beginning assignment. You don't add them, you multiply them. So that's 21 over, what is that, 80? Yep. That's right. Is that lowest form?
No, wait, yes.
Yeah, it is. So that is the compound probability of this event occurring. Yes? Situation 2. 2 cards are chosen at random from a deck of 52 cards without replacement. What is the probability the first card is a jack and the second card is a 10? How many cards are in a deck? 52. How many are jacks? 4. Is that lowest form? No, what is? You just did it. 1 over 13. Now, we are not replacing that card. So how many cards are in the deck? 51. And how many 10s are there? 4. Is that lowest form? Yes. Now how do we do compound? I'll do the top. I'll let y'all do the bottom. What'd you get? 663. Everybody agree with her?
Yeah.
Good. Awesome sauce. Next one, 3. A basket contains 5 apples and 7 peaches. You randomly select one piece of fruit, or erase the word not. Just mark it out, I want to change it up. You randomly select one piece of fruit, do replace it, then you randomly select another piece of fruit. What is the probability the first piece of fruit is an apple and the second piece is a peach? How many pieces of fruit are in the basket? 12. How many are apples? 5. Is that lowest form?
Yes.
Good. We put the apple back. Now how many pieces of fruit are in the basket?
11.
We put it back.
12.
12. And how many are peaches?
7.
We find compound probability by multiplying. What is the answer?
35 over 144.
Good. Everybody still good?
Yeah.
Turn the page. Number 1. Your drawer contains 10 red socks, 8 blue socks. It is too dark to see which are which, but you grab 2 anyway. What is the probability the first sock is blue and the second sock is red? How many socks are in your drawer?
18.
And how many are blue?
10.
Read 8. Is that lowest form?
No.
What is? 4 over. These are blue. How many socks are in your drawer now that you took a blue one out? 17. And how many of them are red?
10.
Is that lowest form? You're smiling, Angel.
Do I check?
Yeah.
Hello?
I cannot believe you just answered it. Is it a telemarketer?
Some random person.
Push your phone on silent. 40 over what? Do your work, but Sarah and Angel. Okay, it's a phone. Y'all all have one. 153. Good. Number 2, an animal cage is holding 4 black cats and 6 white cats. None of them want to be in there. The cage door is open slightly and 2 cats escape. What is the probability that the first one is white and the second one is black? How many cats are in the cage?
10.
How many are white?
6.
3. 6. Is that lowest form?
No.
What is?
3 over 5.
3/5. That is the white cats. The white cat's gone. How many cats are in the cage? 9. How many are black?
4.
4. Is that lowest form? So we are just going to multiply. What do you get? 45. Awesome. We're going to erase the word not right here too. Number 3. Tickets numbered 1 to 20 are mixed up. Then a ticket is drawn at random, replaced. Then another ticket is drawn. What is the probability the first ticket drawn is 3, the second drawn is 5? How many tickets are there? 20. How many are 3? 1 out of 20. How many are still in there because you replaced it?
20.
20. How many are 5? 1. And then you just multiply and you get 1 over 400. Good? And number 4. A bag contains 2 red, 3 green, and 2 yellow balls. What is the probability the first ball drawn is yellow, replaced, and the second ball is green? How many balls are in the bag? 7. How many are yellow?
2.
2. How many are in the bag?
7.
7. How many are green?
3.
What is the compound probability?
6 over 49.
6 over 49. Good. In a box, there are 8 red, 7 blue, and 6 green balls. 1 ball is picked up randomly. 1. What is the probability that it is neither red nor green? So what are you looking for? Blue. How many total are there? 21. And how many are blue?
7.
7. Is that lowest form?
No.
What is?
1
1 over
3.
On the 3.
3. Good? All right, you're not getting homework, so we can try this in.